In order to improve the patch-based ideas we just presented, we need a better understanding of this algorithm and its origins. This is what we discuss next. So how can we bring better theoretical foundations to the patch-based methods we just presented? The answer was given in a paper by Aaron and myself, published in 2006. I remind you that generally, denoising of an image can be done by the map estimate, in which we aim to minimize a function of this form. The L2 error between x and z is a direct consequence of the Gaussianity of the noise. G of x is the prior, and it reflects our beliefs about the ideal image. So who is our G function? Well, our belief is that every patch in the image x has a sparse representation with respect to the dictionary D. Let's write this clearly as an expression for G of x. We sum over all the patches and per each demand that its representation alpha k is sparse, while constraining the representation error to be small enough. In this expression, we are essentially posing many p0 epsilon problems for each of the patches and merge them into one by summing the number of non-zeros in all the representations. Observe that in our expression, we use the operator rk to extract the patch from x in location k. So now that we know G of x, we can describe the full map estimation. It starts as before with the log likelihood term that demands proximity between the image, given image, z, and the desired image, x, and then we add the prior. Here we replace the representation error constraints by penalties. In this optimization, we have two kinds of unknowns. Clearly, the denoised image x is an unknown, but also all the alphas, the representations of the patches. We can optimize the alphas by fixing x. If d is unitary, observe that this is still a simple thresholding for each patch, just as done before. Given the alphas, we can optimize with respect to x, and this is easy as well since the problem is quadratic. Let's present these two steps in more details. This is our problem, and suppose that somehow we have x in our hands. Updating the alphas to minimize the above expression leads to an independent set of pursuit problems, one per each patch of x. When the algorithm starts, we suggest to initialize x by setting it to be z. In that case, the level of noise in each patch is known to be n squared times sigma squared, so we can approximate p0 epsilon to meet this error level. All these pursuit steps are low dimensional. If d is unitary, you might as well remain with the thresholding. For more general dictionaries, we could use the OMP or the basis pursuit. Now let's talk about the update of the image. If all the alphas are given, the expression we face is quadratic with respect to x. The gradient of this expression is given by this linear equation, and after a little bit of algebra, we get to this formula for the computations of the estimated image x hat. You might get the impression that this expression and the matrix inversion in it are complicated, so here are few illuminating observations. First, d times alpha k is the denoised kth patch. When multiplied by rk transposed, it means that we put back this patch in the kth position on the image canvas. The matrix to be inverted is in fact diagonal, and all that it does is to normalize the number of contributions that each pixel gets. And thus, this is almost the same as the patch averaging scheme we described earlier. One difference is the appearance of z in this expression. This suggests that the noisy image is also merged in the averaging by a relative weight mu. So let's summarize by describing the complete algorithm. We start by setting x to be z, the noisy image. Then we apply pursuit for each of the patches and find the representations, alphas. The last step is a patch averaging, which leads to the output image x hat. Think about it. This is exactly the heuristic algorithm we proposed earlier for denoising an image, pursuit on each patch, and then patch averaging. Thus, we are offering here a more systematic way to give birth to this idea. In order for all this process to make more sense, we should proceed and iterate, returning with the updated x to reevaluate alphas. However, doing this is not as easy as you may think. When we operated on the noisy image z, we knew exactly how much noise there is in each of the patches. After updating x, we no longer have easy access to this information. We will come back to this matter later on when we discuss a method called EPLL.